we were looking at disjoint set data structure. Where we want to maintain a collection of disjoint subsets of 1 to n, and to answer a couple of queries. One is that given an element, you want to know which set it belongs to, and we want to merge or take the union of two sets, right? So we saw an array based data structure with some additional information where we could do find operation in constant time, but the union was like log n amortized time, where basically the idea is to merge the smaller set with the larger set, right? Then we got on to the another data structure, which is basically tree based, and we will have singletons are. So in all these data structures, typically on wherever we are doing amortized complexity, we assume that we start with nothing, right? In fact, new nodes are created by this make set operation, and then we'll do unions and so on, right? So now if at some point of time you already have a collection of sets and then you want to move from there, you need to adjust the analysis a little bit, okay? So we're going to assume that we start with nothing, and singletons are created if you want to represent a set X, and whenever you want to do a union, make the root of. So every set is represented by a rooted tree where the root contains the label of the set, and we want to make the root of the set with smaller size or height, doesn't matter, the child of the root of the other set. And what we observed was that in this case, the find operation takes time proportional to the height of the tree, right? Height of the tree where this node belongs to. So you can think of the whole thing as a huge array of parent pointers, where every node points to its parent. So if you want to know which set element number 5 belongs to, you go index into the array location 5, it takes you to its parent, follow through the parent pointer until you hit there is no parent, and that is your root, and that gives you the label of the set, right? So it takes height of the tree time, and we were trying to show, which I will do now, that if you do this heuristic, so this is union by size or height, then we can argue that the height of the tree would be order log n if unions are done by okay. So this is something I wanted to prove and I got sort of stuck. So let's make the claim. Height of the tree, any tree which you obtain through this union process on n nodes is at most log n if unions are done by So we were almost there. The idea is that whenever we add an extra link to this, whenever the height increases, the size doubles is what I want to make use of. So what we will show is that by induction, height is equal to k implies size, which is the number of nodes in the subtree, is greater than or equal to 2 to the k, and the proof is by induction and on k. And k is 0, height is 0, you have one node, so size is greater than or equal to 1. And this is the base case. The induction hypothesis is exactly this for up to k. And when you have k plus 1, so you are sort of stuck here at the induction step, and I was saying look at the last union, but the last union may not necessarily merge two things of height k. But what you do is simply look. So here is a tree, its height is k plus 1. Look at that point of time when the height moved from k to k plus 1. Okay. How did it move from k to k plus 1? Because height doesn't change unless you merge another tree with this of the same height, right? So when, so this may not be the last union, because the last union I might have added somebody with height 5, and I would have just merged it. Okay, so this is this. But if you look at the time, whereas k plus 1 may be very large, height moved from k to k plus 1. The picture was that this guy's height was k, and somebody with height k got attached to it, and then it moved to k plus 1. That's only way the height will increase in either of this heuristic. And by induction, this has at least 2 power k nodes, and this has at least 2 power k nodes, and totally you have at least 2 power k plus 1 nodes. And later on, you might have added more things, but that's okay. That only works in our favor because we want to show it's greater than or equal to k. Because this may not be the last union. So you look at a tree with height k plus 1, and look at that union which made the height move from k to k plus 1. At that time, you can argue that at least 2 power k plus 1 nodes are there, and you never removed anything from these nodes anyway, you would have added more things. Okay. So from here, this follows that if the number of nodes is log n, then height is at most, number of nodes is n, then height is at most log n. So this means that you can do both these operations, because union, if you know the root, it's just constant time, because you maintain the height or the size or whatever. Then you just have to link one root with as a child of the other. So that's constant time if you know the root, but otherwise if you don't know, you have to find, that's going to take. So this means that you have order log n worst case time. And constant for union if you know the roots. Right? And I keep saying if you know the roots, because in a typical implementation like Kruskal's algorithm, you have two nodes u and v, and you want to know whether they are in the same component, and if not, you want to merge them. So there is a step of finding the roots. So if you can absorb it in the find operation, then the merge operation will be constant time after that. Okay, so then what I was telling and what we're going to do today is that with an extra heuristic for find set operation, we can improve the complexity to something substantially smaller than log n. And that heuristic is path compression. Is that you do it during find set. As we move towards the root, make every node in the path a direct child of the root. Right? So you have this tree and your find set operation starts from this node which I am asked to find which set it belongs to. So I will keep following through this path and I will hit this root and I know the label. But after this, what I will do is make everybody in this a direct child of the root. So let's call this child f. So let's call this an x, y, z. So x would be and y would be a child of t and z. So this is how the tree will get changed to. Okay, and it doesn't cost anything extra because anyway, or it just doubles the cost. I'm finding all this. I am traversing this path, so I might as well do something which will help the future operations. So now we want to carefully capture how, clearly it does help future find operations for any of these nodes because now you have a constant time. But how do we capture this interrelation between these operations and argue? And the claim is that if you are doing some m such unions, then the total time is m log star n, or it's actually I told you it's even better than that, but what we will prove is log star n. Okay, so the claim so these are find union where n is the number of elements, number of nodes, or a number of, you can think of it as a make set operation which creates a singleton node. Okay, so n is the number of make set operations. And recall what log star is. Log iterated k times. This is not log power k, but log is less than or equal to 1. How many times you have to take logs so that the resulting number becomes less than or equal to 1, right? And we saw, log star of 1 would be 0, right? You don't even have to take any log because it's already less than or equal to 1. I might have said log star of 2 would be 1 because if you take 1 log, it becomes 1. What about 3? 3 is 2, right? So, okay, so n equal to 1, 2. So, for 3 and 4, log star of n is 2 because if you do log of 4 is 2, another log will get you to 1, and 3 is 1 log will still not get you to 2, 1 yet, so you need one more. 5, 6, 7, 8, all the way up to 16 will get you log star of n equal to 3, right? Because log of 16 is 4, log of 4 is 2, log of 2 is 1. So, if you do 3 logs, 16 will get you to 3. So, that is how these numbers grow. So, let me do a couple of 17, 18, all the way up to 2 power 16, log star n is and then 2 power 16 plus 1 all the way up to 2 power 16. This is 5 and so on, right? Hopefully in practice your n is 2 power 16 is what? 256, right? Or it's even more. 2 power 8 is 256. So 2 power 16 is a lot more than 1000 exactly. And then you're talking about 2 power 1000. So, you're already well within practical ranges of n that, and I told you that the actual running time of this algorithm is even better than Logstar n. Okay, that's the inverse Ackermann function, which grows even slower than Logstar n. Okay, so for all practical purposes, it's constant, but it is still not constant. Okay, it does grow. Actually, yeah, m is more than n, so I'm going to write m plus n times log square n. But m is anyway at least n, so you need to do n make set operation. Okay. So how are we doing find operation? This is how we're going to do find operation. And when we do union, how are we doing union? Now I have to sort of say it here. So essentially we'll do union by height, but I'm going to call it rank. So every root has what is called a rank. So for a node with no children, this has rank 0. And whenever you are trying to merge, so every root has a rank. Okay, and when we create the singleton, the rank is 0. And whenever we merge two things, we always merge. So union, merge or make the root of smaller ranked set the child of the other. And if the ranks are same, increment the root, increment the rank of the root after union. So it roughly represents height, but it's not quite height because path compression is going to change things. So, but every root has a number rank which we maintain and update according to this rule. When you create this node, rank is 0, and whenever I'm merging two nodes, two trees, I look at the one which is smaller rank and make this a child of the other one. If the ranks are the same, decide arbitrarily, but the new root's rank is incremented. Okay, so this is just a mechanical rule, if you like. It roughly corresponds to height, but it may not because the path compression is going to change things. So the rank is going to play a role in our proof. So that's why I want to define and mention this rule. So now we do the unions like this, and we do the finds like path compression. Let's make some observations for rank. Okay, so some properties of rank. Rank of X is strictly less than rank of its parent, right? Unless it's a root. Okay, so this is parent, right? The way we actually do the unions, this is true, right? Because you always make the smaller one make child of the other one. If they are equal, you increment the root anyway. So after that, so the ranks are in a path, ranks are monotonically increasing. Okay. Number of nodes. So now, in one tree you can have lots of different, lots of nodes with the same rank. I want to claim the number of nodes with rank r is less than or equal to n by is this clear? This claim is going to be useful. So suppose I did not do path compression or anything, then its rank corresponds to height, and whenever a node has a rank r, we already have seen that it has at least 2 power r nodes in that tree. So that means any other node in this tree cannot have rank r because of that claim, first claim. Okay, so these 2 power r nodes cannot have rank r. So the number of nodes with rank r can be at most n by 2 power r. Right? For every node of rank r, you can sort of throw away some 2 power r nodes. Okay, so the rank doesn't change when you do path compression. Okay, the nodes change and so on. This is the only way the ranks are updated. Okay, otherwise the rank is just a number associated with every node. It roughly corresponds to height, but path compression can move things around. But think of it as just a number associated with every node. Okay, so number of nodes. So the proof is that for every node with rank r, and you can also see that in a perfectly balanced rank, if it corresponds to height, is one node with height log n, 2 nodes with height log n minus 1, right? So that's n by 2 power r. If you plug in r equal to log n minus 1, there will be 4 nodes with height log n minus 2, and that's what this corresponds to. And if you plug in log n minus 2 here, it will be 4. Okay, so that's all I need properties of r, and then we are ready to do our analysis. So how am I going to do the analysis? This is my claim that so we are going to just talk about find operation, because the union operation involves just finding and then doing a union. So it can be translate every union as like 2 find operations followed by some constant time link operation, right? So I'm going to talk only about find set operation. Now, so come back to our credit based thing, that every find operation is going to come with some Logstar and credit. Okay, but the height it's going to traverse may be very large. It could be as bad as log n. So it's going to pay using this Logstar n for some part of this axis, and for the remaining part of the axis, as happens in amortized complexity, we are going to use it from the potential of the data structure, right? So we'll do it slightly differently. So what we are going to do is, this is same as the potential argument, but for every find operation, you have to spend time proportional to the length of the path. For some parts of the nodes accessed in the path, I will pay the union find operation will pay from the credit it is bringing. For the remaining, I will put some credit on the remaining nodes, okay, which I will add later on and compute it, and that is the overall time, right? So, yeah, I can remove that. So we are doing this proof of this claim now. So first we will confine to find set operations. each such operation comes with Logstar and credit, right? But such a find operation is just going to access a long path like this, right? So the actual time is proportional to the length of this path. So I'm going to use the Logstar n to pay for maybe this node. I'll tell you exactly what that rule is. And for the remaining, I'm going to put one credit. Okay, which means that this is something I should count later on. This is the time, right? Now some other find operation will access some paths and it will add more credits to these nodes, and eventually my total time would be, what would be the total time? M Logstar n, because each operation is coming with Logstar n, plus collect all the credit in all the nodes here, and that's my total time. Right? I'm just sort of distributing the cost of my each operation, saying, okay, here is the cost. For some nodes, I will use my credit, and for the remaining, I'll just put, usually we take from the data structure, we're going to putting it on the data structure. Other way to think about it is, imagine there is a Logstar and credit on every node in the tree. Then you can take it out. So that's another way to think about it. But let's use this way, that every operation, if so it's sort of accounting. I will use my Logstar n to pay for some nodes. For the remaining nodes, I'll put a note saying, okay, I have to count you later on for my time. And some other things will add more credits. So my total time would be M Logstar n plus the sum of the credit on all the nodes. Okay, and I will argue that no. Okay, I was going to say that every node gets at most Logstar n credit, so it will be M Logstar n plus N Logstar n, but that's not exactly the case. Some will have more, some will have less. We'll come back to that. So this is a strategy, okay? And how am I going to charge it, right? Okay, so now we're going to, I have to bring in Logstar n somehow, right? So I will divide my ranks into various groups. What is the maximum rank of any node? Right? R is actually at most log n, right? Because we have seen that. Because if you have a rank R, it will have at least 2 power R nodes and so on. So let's even use n, okay? I think it's convenient to use n. So every node has certain rank between 1 and n, and I'm going to distribute them into various groups. How many groups? Group the ranks actually 0 into Logstar and groups. How am I going to do it? It's exactly like this, okay? Yeah. So group 0 contains rank 0. Group 1 contains rank 1. Group 2 contains rank, yeah, okay. 3 and 4. Group 4 contains rank 5, 6 up to 16. Group 5 contains ranks, these are ranks, right? 17 to 2 power 16. So if I have to write this more precisely, it will be 2 power, okay, so GR no, 2. something like this. So essentially, if you are rank R, you are sitting in group log star R, roughly plus or minus something. Okay. So I'm just distributing the ranks. The ranks could be up to 0 to log n. Let me go all the way up to n, and I'm distributing the ranks into various groups. That rank 0 will be in group 0, rank 1 is in group 1, and essentially, if you are a rank, then you will be in group log star of R. Okay, because this corresponds to this log star. Maybe plus 2 or something. Because log star of 2 is 1, I am putting it in 2, and 3 is 2, I am putting it in 3. So rank R belongs to group G log star of R plus 1. Okay, so this is just a distribution of groups, and so one way to think about it is if you look at this whole tree, there are various ranks. In a path, ranks are all monotonically increasing. I've just divided the ranks into various groups. Okay, so now I'm going to charge my find set operation using the credit I'm bringing in sometimes, and sometimes I'm going to put credit on the node. When am I going to do what? Let me give that rule here. So use your credit if G of rank of X is not the same as G of rank of parent of X. So in the path, right? X is some node. I'm going to account for all the nodes that I encounter in my path for my cost, right? So if X is a node, I look at what group your rank belongs to and see what group your parent's rank belong to. If they are in different ranks, then I'm going to use my credit to charge for that node. Okay. Now, is it clear that Logstar n credit is enough for this? Because I removed, there is property 1 which is there. The ranks are monotonically increasing. As I traverse my path from this node all the way to the root, the ranks are monotonically increasing. So, a whole bunch of nodes ranks will form in the same group, and when I jump from one group to another group, I am going to use my credit for this, right? But how many groups are there? Log star n, right, plus or minus 1. So, I use my credit, which is log star n, when my parent's group and my group are different. Okay. Otherwise, I'm going to put some credit on the node. Right. Else, put a credit on other nodes. So what are we trying to do? Somehow path compression shrinks a lot of paths, and somehow I want to capture this, and so. And what I am doing is that whenever my parents ranks group and my ranks group are different, I charge it to me, and the remaining times I am going to put credit on the nodes. Okay. So clearly, how many times this jump can happen? Log star n times, because there are only log star n plus 1 many groups. So log star n plus 1 is enough for my credit to pay for these things. Now, all we are left to show, what do we have to show now? So this is it, right? This is my charging for one fine set operation. It just traverses the path and uses the credit to charge some nodes, and for the remaining nodes it puts some credit. Now another fine set operation comes and it does something. So overall I have done some m many fine set operations, and I have to count the overall time. I already spent m Logstar in time. Now what I want to argue is that you count all the charges left on the nodes now. They together add up to at most n Logstar n. Okay, that's what we have to show. So all we need to show at the end of these m operations, total credit left on the nodes and let's look at a node and see when does it accumulate. So suppose you have a node which is sitting here. So this is the entire group, okay, the group of ranks here, and this node, it gets some credit. Why did it get some credit? Because some fine set operation touched it, and that node and this guy are in the same group. Okay, but remember, after the fine set operation, this guy is going to move somewhere. Everybody is going to move up, right? So its rank will increase. You know, everything in that path, the rank will increase, because sorry, not the rank won't increase. Its parent's rank will increase. It's okay. The ranks don't change at all, right? I said, but the parents change because of the path compression. Hence, parents' rank can be different, and it will increase. Parents, because you are moving up, so this guy's rank doesn't change, but its parent was, so this guy's parent was this, but now its parent is somewhere else. It will have so its parent will have a higher rank. Okay. Not yet. Yes, but more unions may happen and so on, right? Yeah, right. So the important thing is it's the parent's rank is going to increase, because simply because parent moves up, because that's where we use the path compression, and so and in a path the ranks are monotonically increasing. So this rank will, its parent's rank will increase, because this was its parent, but now this is this parent. Maybe after it gets more credit, one more fine set operation may move it even above, right? So how much credit can this node collect, right? Eventually, if it reaches the top of the group, then its parent will be in a different group. So I will no longer accumulate, because now for accessing me, the fine set operation, they come with the charge, and that's what is being used for. Because whenever the parent is in a different group, parent's rank, I won't, I'm not charged. So the amount of credit I'm going to accumulate is that for any node, I want to claim that it is at most the number of ranks in the group. Okay, so that's a claim. Now here is a claim. The amount of credit on a node X is at most number of ranks in X's group. Because after accumulating one credit, X's parent rank increases. Okay, so after every credit, okay, that's a proof. rank of parent of X increases as X's parent changes due to path compression. And it stops getting credit once its rank is the largest rank in the group. Because then its parent will be in a different group. Parent's rank will be different. So it can start with the lowest rank in that group and the parent, and eventually it can move up after every time it gets credit. So the number of ranks in that group is what it can accumulate. Okay, so that's the argument. Now you look at the groups, you know how many ranks are there, right? Because initial groups have small number of ranks, but after that there are a large number of ranks. So this group formation and this property will help us complete the proof now, okay, and this claim. So now I've done all my fine set operations. I've computed the total time each fine set operation comes with, and now I tell you, I have a general statement on if you look at any node, how much credit it can have. Well, how many ranks are there in its group? That is the amount of credit each node can have, right? So they are distributed. Not everybody will have the same amount of credit. But now I want to argue that overall this number is like n log star n. And the way we will argue is that if you look at one group, the total credit would be at most order n. Okay, and the number of groups is log star n, and then we'll be done. Okay. So let's first count the number of nodes in a group. Let's say in group number R. Okay, so I'm going to erase this proof. So let's next claim. Let's fix this group GR. Okay, which has ranks this plus 1 to this. This is the range of ranks which are sitting in this group. So any node from this, because of this claim, any node in this group two power r credits. More precisely 2 power r minus 2 power r minus 1 credits, but I'm even going to ignore this because that's the total number of ranks in that group. Because this claim said any single node, how much credit it can get is the total number of ranks, because the parents, rank keeps increasing after path compression. And the number of ranks in this group is 2 power r minus 2 power r minus 1. So let me even ignore this. It's at most this much credit any node can have. How many nodes are here? This many ranks are here, but how many nodes are in this group? For each particular rank, there are so many ranks. For each particular rank, you can have at most this many nodes, right? So let's do a calculation. Number of nodes in GR is at most. So let me just call this okay. So let's give okay just some notation to simplify my 2 power 2 power thing. Then what are the ranks here? Ranks in GR in the range are yep yeah.
Why is the number of nodes ranging from 2 raised to 2 raised to r minus 1 plus 1 to 2 raised to r 2 raised to 2 raised to r? Shouldn't it be 2 raised to r minus 1 to 2 raised to r minus 2 plus 1?
So first of all, it's not the nodes; it's the ranks.
Yeah, the ranks.
Okay.
Why
Yeah.
ranging from 2 raised to r minus 2?
Plug it in and see, because we are talking about Logstar, right? We want these groups to correspond to Logstar.
2 raised to r minus 2 plus 1.
Oh, that's how it's supposed to be. Okay.
2 raised to r minus 2 plus 1 to 2 raised to r minus 1.
Okay. Is that fine? So when yeah, right? Yeah, his point is when r is 5, you should have. No, it was right. I think it was fine, right? So when r is 5, what we had was sorry.
It should be 2 raised to r
R minus
2 raised to r minus
yeah, okay. Yeah, okay, fine. Yeah, I go all the way up to 2 raised to r minus 1. Right. Is this fine?
I'm saying it should be 2 raised to r minus 2 plus 1, not 2 raised to 2 raised to r minus 1.
No. There is 2 raised to 2 raised to, because you have to connect it with Logstar. The last term should be 2 power whatever the last term was. I'm clear about it, because then that's the extra log. You have to take one log to get here and then another log, and then you get here. So this last term must be this. So for G5, it was 2 raised to 4. Yeah, so 2 raised to r minus 1. Yeah, because it has to correspond to Logstar, and if you think about it, if you take one log, you are already here, and then you're adding 1. Yeah. So the last term must be 2 raised to 2 raised to, and then you can work backwards to see what it should be here. Okay, so where were we? So I said the ranks in the group R is exactly from r plus 1 to 2 power r, right? That's what. Now I changed something. So this. Yeah, let r be 2 power r minus 2. Then I'm going from r plus 1 to 2 power r. Now let's compute the number of nodes in GR. Well, if you fix any particular rank, we know the number of nodes is at most n by 2 power blah blah blah. So this is at most n by 2 power r plus 1 plus n by 2 power r plus 2 plus n by 2 power r. But this is again a geometric series, so the leading term dominates. You can just multiply by this. So this whole thing is at most 2 into n by 2 power r plus 1 So it's n by 2 power r. So I have to adjust this also, 2 power r minus 1 minus 2 power r minus 2. So I'll rewrite it. Okay, so is this clear? And then I'm going to copy it more properly there. So we fixed one group and we have ranks in a particular range. And you know, for any fixed rank, the number of nodes is at most this much from that second property. So you add them all. And this is a geometric series. I'm just going to lead it by the first term multiplied by 2. Right? This into 1 plus half plus and so on. So that's, I'm just 2 into this. Okay, so let me summarize and say what I. So what is my claim? Number of credits in a node in GR is at most the number of ranks, and the number of ranks is 2 power r minus r. So I'm going to write it as 2 power r. Number of nodes is at most n by 2 power r. So total credit in your group GR is at most okay. Let me pause for a minute and make sure everybody follows this. So this claim is a key thing which uses the path compression. It says that my parent will keep on changing and eventually its ranks will increase to the point that it will go to the next group and I will start accumulating credit anymore. How far that happens is that number of ranks in the group. And if I fix a particular group, the ranks after my adjustment is this to this. Yep.
Here R itself is 2 raised to 2. The GR, like the range
Yep.
can raised to 2 raised to 2
Yep.
Like as you said, like that was
Oh.
it should be here the lowest range should be just 2 raised to r minus 1. To the highest range is 2 raised to 2 raised to r minus 1.
Aha. So
17
this
is also like 2 raised to r minus 1 plus 1.
correct.
And GR should be like that. Because otherwise the last term should be triple.
Okay. Okay. Yeah. But it is what it is.
In G5, 17 is actually 2 raised to.
Whatever this, yeah.
So 2 raised to, if G5 we are taking it as GR, then 17 is 2 raised to R minus 1 plus 1. So 2 raised to 4 plus 1.
Okay, but then this has to be 2 raised to 2 raised to 4.
That should be like that.
Yeah, okay.
2 raised to 2 raised to R minus 1. The last term is that. The first term I think it is. Okay, then.
No, but this is basically, what is this? This is 2 raised to 2 raised to r minus 2. Because r minus 2 here is 4.
So when it comes to the next group, then same happens.
Yeah, so it is what it is. It does grow such, that's the whole point of Logstar, and it does grow fast.
R was 4 minus 2, and the next one is 5 minus, which is not right.
No, whatever I have, 2 power that is the last term here. And plus 1 is the first term. Okay. So let's now reverse engineer and see what it is, right? So it will be the towers of 2. I mean, that is going to happen because that's how Logstar is defined. And so what is the problem here? So maybe the last term is not correct, I think. So when R is 5, so this is 2 power. Yeah, it's probably even not even, so I should have more powers of 2. That's the point. It's not even, 2 power, something like this. Yeah, it is this, right? 2 power 4. Yeah. So it is not 2 power r minus 2, but towers of 2. Okay. So it's towers of 2 some r minus 2 times. Yeah, and then the towers of 2 r minus 1 times. Okay. So I need a good notation for it. So I think this is fine. Whatever r is, so whatever r is, so I'm not even going to define r. So the ranks in a group is going to be something like r plus 1 to 2 power r for some value of r, which is a tower of 2, right? Some tower of 2. The important thing is that the number of credits and the denominator and the number of nodes cancel out here. Okay. Yeah. So okay. So good point. So this is not quite right, but you need to fix it by. Yeah, define your last term of your group as some capital R, and then it's this. Okay, so it's all towers of 2. That is correct. That's correct. That's I haven't used it yet. Yes, that's correct, because that's the way we define the groups, right? So basically, if you have a rank, you put it in its Logstar value and plus 1, and that's the group number. And it's plus 1 because we started with G0 and stuff. Towers of 2. Yeah. So this should be. But the important thing is that the group has a certain range, r plus 1 to 2 power r for some value r, which is a tower of 2, which is not going to play any role here for us in the argument, but it's a tower of 2. Now the number of nodes in GR is this plus this. So it's n by 2 power r. And the amount of credit anybody in this group can take is at most 2 power r minus r, but I'm even ignoring r, so it's at most 2 power r. And these things cancel out, and you get n. Total credit in one group in the whole process. So this, the Logstar is defined in a way that these things cancel out. Okay? I mean, why did we even think of groups of Logstar n? Because that's the way we divided the groups. 2 power the end point of the rank is the end point of the next group. Now, if you adjust it differently based on Ackermann's function and define the groups, you essentially get the inverse Ackermann proof. So this Logstar n is the inverse of towers of 2. And so we use towers of 2 to define our ranks. So if you use the Ackermann functions to define your ranks, what you get is the inverse of Ackermann function as the bound. Okay, so are we done with n? n Logstar n. Are we done? What did we show? What have we shown and what is left to do? There are Logstar and many groups, right? So all we've shown is that in one group there are lots of ranks. So basically what it's saying is that if there are lots of ranks in my group, then the credit will be large, but the number of nodes will be small. Because R is large, number of nodes is small, but credit will be large, but they all cancel out, balance each other. So it's not that uniformly every node will have the same amount of credit. No, the whole group will have credit of n. And the number of different groups we have is log star n. So total charge on the nodes. So number of groups log star n plus 1. So total charge on the nodes is at most n into log star. And there are some nodes which we did not count. Anybody whose parent is in a different group, but that is charged in our m log star n. So total cost and that's what we wanted to show, right? So the amortized cost is only log star n calculation. Yeah, so the main idea is that the ranks are monotonically increasing and number of nodes with the rank is, if you're talking about a large rank, number of nodes is small. Small ranks, number of nodes could be large. And we divide the ranks into various groups, and every operation comes with a log star n credit. So basically one node for each group is what it's allowed to pay. And the remaining nodes, we put some charge and overall count that it becomes n log star. Yeah, and as I said, this n by this 2 power r and the ranks, we define them based on 2 power r. They have a correlation to cancel out. But if you define based on Ackermann function, you get inverse of Ackermann as the bound. Okay, so this is, and I also mentioned that there is some lower bound of inverse alpha n. So all this is due to torsion in late 70s. And there have been later work which tried to simplify, provide more insight into it, but different kinds of charging argument. But we know that the inverse alpha n is the best we can do. Okay. Yeah. So that's all I wanted to say on this disjoint set union data structure. Yeah, so I'll spend maybe 10 minutes talking about the next amortized structure we want to talk about. And that is binary search trees. So recall what a binary search tree is. It is a data structure that supports efficient insert, search, and delete in logarithmic time, balanced binary search trees. And so it is a rooted tree with values on the nodes satisfying what is called this binary search tree property, where okay, so this would be okay. I'm just checking whether you're awake. So this is not a binary search tree. Why not? Because on the right side, you need values to be larger than the root. So 85 is not. I can't make it 185 also, right? 101. Okay. So that's a binary search tree. And it is useful for search clearly, because if you want to search for an element, you compare it with the root, and if the element you are looking for is larger, you go to the right, otherwise you go to the left and recurse, right? And the time for search would be proportional to the height of the tree. So you have every reason to do your operation so that the height remains order log n. So there are many balanced binary search trees where ABL trees, red black trees. There is something called B trees. So B trees are nodes where each node contains more than one value, right? It will have many values. But then how do you want to maintain the search tree property? Suppose instead of keeping one value here, suppose I keep 3 of them, then how do you want to maintain your search tree property? The left smaller, the right bigger thing is no longer true, right? Left is bigger, smaller than what, and the right is bigger than what, because there are now 3 values. Yeah, I have maintained in sorted order, but I want to know this property of the left being smaller, the right being bigger. Smaller than what, bigger than what? Hmm?
73 can have a left child which has all the values smaller than 2.
Okay.
And the right side value to 73 will have values between 73 and 80.
Okay. And then that's all?
Yeah, and similarly.
Yeah, so basically if you have I values, you should have I plus 1 children. Okay, this is one of the properties of B trees. Okay, if you have I values, you should have I plus 1 children. So since if I have kept 3 values, then I should have 4 children. So anything here is less than 73, anything here is between 73 and 88, anything here is between 88 and 200, anything here is bigger than 200. And you proceed, recurs, and so on. So there are these 2, 3 trees where, so B trees have a very specific property of how many nodes, how many children, there is a range of children allowed, right? B tree of order I means that you can have between I and 2i values or something like that. So there are some specific set of properties, invariance being maintained, which helps you to search in logarithmic time. And whenever you do insertions and deletions, you also maintain those invariants. How do you maintain those invariants? Using what is called a rotation, right? So in heaps, for example, whenever this violation happens, you do some swaps. Here what you do is rotation. This is important. Let's do this. So, right? So if I have a binary search tree like this, now if I want to right rotate at x, maybe let's do left rotate at x. So basically we will do this rotation like this. Okay. So that means A goes up and X comes here. So if I look at this, so I am doing X here and A here. Now where would the children lie? They have a natural place. It should come in this order: Y, B, C. So Y would be here, B would be here, and C would be here. Now this could be a big subtree for that matter. So you just put this subtree here. This is the left rotated X. The important thing is that if it was maintaining the binary search tree property before, it will maintain it now also, because why? Let's verify this. Anything here is less than X, and that's true here. Anything here is greater than X but less than A. So anything here is greater than X, less than A, and anything here is greater than A, and that's true. Okay. And so this rotation operation is an important operation. It's done to make sure it's a constant time operation, because you're just doing, one ancestor child relationship is changed, maybe more, but you maintain the binary search tree property and you do some balancing in the process, so that somehow the height changes. So all these, and similarly you can define right rotate. So Y will come up, X will come down, and then you stick in the remaining subtrees exactly the way in which they're coming. So all these ABL trees, red black trees, B trees, and a whole variety of them maintain certain invariant on the heights to make sure that the overall height of the tree at any point of time is logarithmic in the number of nodes. So search remains logarithmic, and whenever you do insertions or deletions, there's a whole bunch of cases to make sure that you do some rotations to maintain the invariant. Okay, so if you have not seen them, it's worth checking them out. At least one of them. B trees are good for some reason. I don't know whether anybody has seen it, and it's an interview question, right? So what is good about B trees? So if I have, so let's say I store, B tree. Suppose I make, make the fan out or degree very, very large, right? That means what happens to the height? The height comes down because it's log n to the base of the degree, right? So do you search much better than log n then? Because the height comes down, right? Do you get a search time better than log n to the base 2? Yes? You have to do more comparisons at each node, right? How many comparisons would you do? If the number of nodes is k, so I'm searching for a node, and I already told you if there are k nodes here, I have this partition of my entire set into smaller than this, those in between, and things like that. So now first you have to figure out which subtree to go. How much time would you do? Log k many time. You have to do binary search to figure out where to go, and then keep doing it. So it's log k times log n to the base k. So it's log n. Okay, so you're not saving much. So what is the saving? Why is it good? So B trees are really actually some of the industrial databases use B trees. Why? Because it's very useful for external memory data structures. Right? There are situations often where you can store an entire set of nodes in your main memory, where the search is not a big deal. What is the big deal is you have to go and access from an external memory, right? So what you want to do is to minimize the number of these external accesses. That corresponds to the height of this tree, right? So you take each node in your main memory, then you will do your binary search, which is cheap. I'm not going to even account for them, and then I figure out where to go and bring which page. So the number of external memory accesses is proportional to the height of this B tree, and so if your fan out is large, then the height is correspondingly smaller, and it helps in external memory. So in fact, some Berkeley DB, there are some data structures which actually use this heavily B trees with a large degree. Okay, so good. So there are all these balanced binary search trees where we can do these what are called dictionary operations, insert, search, and delete in logarithmic time using all these rotation operations. So what Slater and Tarjan proposed is that I'm not going to do any invariant to maintain balance. So these are called actually self-adjusting binary search trees. This is also splay trees. So it's a binary search tree. Now, let's say you are searching for some element and you ended up here. So other than key values, we don't store anything. Okay. AVL tree stores some information about which one is, whether the right is bigger or the left is bigger. Red black tree stores some color information. So here no such information other than the values and the left pointer, right pointer, nothing else is stored. Now if I want to access this, somehow some search landed me here. What they proposed is do some rotations and do some rotations. Basically that's there. They gave a very set of controlled template rotations. So for example, they'll say to look at two nodes at a time, the node and its parent and its grandparent, based on the shape of that, right? It could be any of these kind of shapes. That's all, right? These are the four possible shapes the parent and the grandparent can take. Based on that, they said, okay, if you hit this, do this rotation. If you hit this, do this rotation, right? So after doing this rotation, this node will come here now and perform again, look at its parent and grandparent and do this rotation. So it is sort of like the path compression, right? Where anyway you are spending so much time to go and do your find operation, make everybody a child of the parent is what path compression said. And what here they said is do some rotation so that this node becomes a root. Along the way, some restructuring of the node happens, of the tree happens. And then they argued that this automatically somehow balances the tree, that if you look at the amortized complexity of insertion, deletion, and searches, it's logarithmic. Okay. So we will look at this specific template, what they asked us to do the rotations, and look at the proof why this gives you logarithmic behavior. And there are lots of conjectures, open problems around it. So we'll see all that next time. Questions? Okay, so I don't want to start that now. Just given you a flavor of what is coming. So we'll do it next week.